Okay, welcome everyone. I'm going to give a talk here, or I'm going to record now a talk which I gave about 1.5 weeks ago live. And I really come to the conclusion that sometimes it's better if you give a live talk and there are no amenabilities to really record the talk. I could do that myself. Obviously, I have a camera here right in front of you, right in front of you. Obviously not right in front of me. But I kind of just the quality always is a bit quite questionable. Not saying that this quality is better, well, it's not questionable, but it's certainly better. So I usually went to kind of record talks after I gave them. It's also better for the local audience because then I can just focus on the talk. Okay, so I'm going to give a talk, which I already gave. And well, there is some sacrifice I need to do. And the sacrifice is there won't be any live questions and live interactions, obviously, because this is now recorded. I hope that works for you. But anyway, the topic I've chosen is actually quite nice, but somewhat well known, but not well known enough, in my opinion. That's why we're here. So it's about the four-color theorem, or rather the three-color theorem. That's why I have my three-color suffice here. Maybe I get this in red to make it easier to see. The three-color suffice. So it's about how to reformulate the four-color theorem using three colors only, and then going even one step further and reformulate it in terms of representation theory of a certain type of object, which I call special orthogonal 3x3 matrices, or SO3 for short. And all I'm going to say is essentially well known, as I said. So my contribution is like 0, but it's still kind of not that well known, which is kind of a little bit funny. And I really love it, so I'm going to explain it. And yeah, so it's all about the four-color theorem, which, well, I will recall it, obviously, but it's kind of one of the key theorems in mathematics altogether. And when it was finally proven, the US Post made a stamp four-color suffice, and I just took that as my thumbnail here, and I decided to go with three-color suffice, which is really kind of the topic of my talk. Okay, so yeah, this talk was given in January 2024, which depends when you watch this video, might be a million years ago. Oh, this is very good. So might be a million years ago, or well, when I'm recording this, as I said, it's just like 1.5 weeks ago. So I gave it live at a UC combinatorics seminar. Thanks for having me. It was a lot of fun. Okay, I start recalling the four-color theorem. So the four-color theorem for me is exactly what you see here. It's a coloring of a map. Could be the world map. Here is my world map. And I'm going to color it with colors such that bordering countries, neighboring countries get different colors. So let me just say here, Canada and the United States are neighbors, so they get different colors. So task, color my countries on any map, essentially, not just a world map, on any map you can hook up, such that two countries that share the same border get different colors. And in this my picture above here, I actually consider the ocean as a country. So the ocean gets color blue, so only landlocked countries can get color blue as well. For example, whatever those landlocked countries are, here in Africa, or this one here. Yeah, so landlocked countries can get color blue and no other country can get color blue. Australia, for example, where I'm recording this, can't get color blue because Australia is like obviously not landlocked. Anyway, hope the task is reasonably clear. So this is a really, really famous kind of idea, and I'm going to explain the history in a second. But essentially the question is, how many colors do we need? And by do we need, I don't mean for this one map that you see in front of you right now, so not for the world map, but varying over all maps. So is there kind of a worst case possibility for the number of colors you need? That's not quite obvious because we vary over all maps. So there could be a priori, there could be a map which needs 5 colors. A priori, there could be a map that needs 6, 7, 8, 9, 10, 11, whatever colors. Not quite clear. What is, however, fairly easy to see is that you need at least 4 colors. So when I was giving this talk, I was in California, so I found this one kind of really useful because California is the existence of California, if you want, is an obstruction for a 3 coloring of the world map, or not of the world map, in this case of the map of the states of the US. Because if you consider Nevada, it has 5 neighbors, including California. And if Nevada gets color yellow, then all of its neighbors need to get a different color, but they are bordering one another in an alternating fashion. So you give the Utah green, Idaho blue, Oregon green, California blue, and then Arizona plays a party pooper and you need the fourth color. Maybe this map is a little bit easier. So whenever you have a map in the middle, sorry, not a map, a country in the middle, and whatever its neighbors are, if it has an odd number of neighbors, then we really need 4 colors, right? So an odd number of neighbors and we will need 4 colors. If it has an even number of neighbors like here, 1, 2, 3, 4, 5, 6, 7, 8, then you could alternate, but as soon as you have an odd number of countries, you need at least 4 colors. And as I said before, not quite obvious why there's an upper bound. I just told you there's a lower bound. And the whole point of the 4-color theorem is that the lower bound is the upper bound. So the story is actually a little bit sad. There was a person like 100 feet, let's say 150 years ago, I can't count anyway. So quite some time ago, who was forced to color the counties, analog of countries in England. So here's a map of the coloring of the map of the counties of England. And this is already a boring task. And it was exactly the task, like give different bordering countries a different color. And they got a little bit bored. Like, this is a little bit of a boring task, is it? And then they're trying to play this game with how many colors do I actually need? And they came up with, I can't do better than 4. So maybe I need 4 colors. And then they thought about it for general maps. And they realized, can't construct a map where I really need 5 colors. So maybe 4 colors suffice. So that's where the conjecture came from. And what do you do in 1852 if you can't write an email, if you can't ask Dr. Google? You write to your favorite neighboring mathematician. In this case, you write a letter to this letter here, which is signed like October 1852, and you just send it to your favorite closest mathematician, which in this case was the famous De Morgan. And De Morgan was like, well, I don't know what De Morgan really did, but let me just think that De Morgan was like, this is easy, I can prove it. Thought about it for a while, couldn't prove it, and then popularized the question as, we as mathematicians should be able to prove it. And it turns out that this question is like so innocent, right? You're coloring neighboring countries, and you just ask how many colors you need. Looks very innocent, but it turns out it's like really, 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 really difficult to prove. And many mathematicians, many really brilliant mathematicians, gave wrong proofs or gave up eventually. And it became one of the most annoying questions in mathematics, actually, because it's so easy to state, and then it's so tricky to prove. And we'll see, actually, a kind of proof which almost gets you there. So to almost get there is actually quite easy. To almost prove the 4-color theorem is not so difficult. Many people did that, but to really prove it is like really, really, really difficult. Yeah, and the famous proof where we had to post-stamp 4 colors suffice is referring to, well, the proof of Appel and Haken, which is like, later they published the proof in a book. I'm just talking about the book, not the original one. I should do something about this. They're not talking about the original one. And yeah, the book is from 1989, and it is like 700, it's like, let's say 800 pages long. Yeah. And roughly 500 pages of this book are cases to check, not checked cases. No, there's still a check involved. So it's cases to check. It's kind of fun. So the appendix of this book is like 500 pages of what we need to check. And it turns out the 4-color theorem always needs a lot of little cases you need to check. That's why it's so difficult for all of these exceptional type of cases. And yeah, this was the first major theorem that was proven using a computer because there are just too many pages and too many special cases. There are 500 pages of special cases. And in each special case, you still need to find the coloring. It's like really, really, really difficult. Anyway, so this was the first computer-assisted proof, and people got really upset about that. Classically, mathematicians wanted to prove everything by hand. And nowadays, everyone is happy with a computer proof. Actually, nowadays, I would say a computer proof is actually better than a human proof because humans do mistakes. Computers only do mistakes if the human does a mistake, essentially, who was programming the computer. So nowadays, I would prefer computer proofs, and this proof is computer verified. But anyway, at that point, it was kind of a huge big deal. But finally, it was proven, and it eventually gets accepted. Like everything is kind of weird if you see it for the first time, but if it's just the right thing to do, maybe it just takes a new generation of mathematicians and everyone is happy. Anyway, I will show you a different proof, which is different. It's really different. You check different things, but you still can't avoid a computer proof. And I'm kind of really skeptical about with the four-color theorem. Probably every proof we will ever find. It's very dangerous to say in a video, of course. Life might prove me wrong. I would be happy if someone proved me wrong. But anyway, I kind of believe that every proof you will ever find has some computer component because there are just too many special cases. And the different proof I'm going to show you still has many, many special cases. Essentially, what it does is instead of having like 1,000 cases, like in the Apple-Hackett proof, I have more cases, like 30,000, but I have some question that is somewhat easier to check. So more cases, but an easier check. But still, 30,000 whatever thing cases is just too much to do it by hand. Before we go to the alternative proof, let me just tell you what mathematicians did. Essentially, right after right after the problem was posed, is you turn it into a question about graphs, about coloring of neighboring vertices of graphs, because that's somewhat easier. For example, there's this funny story, which is kind of really, really famous somewhat, why this is important. So if you look at the counties of England, so here's a county, the yellow one here, which I marked with a cross, and there's a green one here. And you wonder whether they're actually bordering or not. It's not so clear whether there's a border between them or not. It's really not so clear at all from the map. And this is why you want kind of a graph. A graph like that here above, every country gets a vertex, and you connect them if they're neighbored. Your graph is kind of a better representation because you can just read it off. So in this case, there's this funny story that here, Northamptonshire here, which is the yellow one, is actually really bordering a Lincolnshire, which in this picture is the green one. And the only reason it is bordering Lincolnshire is because otherwise it would be twice landlocked. If it's bordering Lincolnshire, it's only once landlocked, right? It's only once landlocked. Here's the sea. It's only once landlocked. You can go to Lincolnshire and then go to the sea. And landlocked countries in the UK get a tax reduction, I think. And yeah, well, if it's twice landlocked, it would get a bigger tax reduction. So you add as a government, you add a stupid 20-meter border here, which is like in the middle of nowhere, which doesn't make any sense because nobody ever will pass there, but it's just to make it just once land. Anyway, the point for me is in the graph, you can't miss that because there would be just an edge between the two. But in a real map, it's not so clear, right? It's not so clear whether it's bordering. So that's why, but that's another reason. That's one of my favorite reasons, actually, why people should really look at graphs. Because a graph is kind of a model representation of a problem here of our map coloring problem, but it's somewhat easier to see than on a real map. So I will switch to graphs right now. I hope that is kind of, in this channel, this is probably fine for everyone, but I just wanted to tell this story because this is one of my favorite ones. Why you really want to make an abstract problem where you have a graph and not a real map. Even on this zoomed in map, I can't really tell whether there is a border or not. Honestly, I can't. Anyway, doesn't matter so much. My favorite story here. Okay, and enter Tate now. Tate's, I will explain now Tate's alternative proof. And this is going to be annoying here. I don't know what's going on actually. Anyway, I just continue and it will pop up several times again and I will just barely ignore it. I will just ignore it. Fine. Okay, so Tate's proof roughly works as follows. First of all, you can restrict to triangulate it. So in this case, if you go to graphs, the correct notion is every planar graph has a 4 vertex coloring, and the vertex coloring is just the same as the map coloring. Neighboring vertices get different colors. And first, Tate's first reduction or first formulation is that you can restrict to triangulated planar graphs. Why is that? So here's a triangulated one. So every face that you see is a triangle. Yeah, and whatever the outside is, doesn't matter. Just in this local picture, every face you see is a triangle. And here's a not triangle. Here it is a 1, 2, 3, 4, 5 that are pentagon. But if you find the 4 coloring then for the triangulated graph, then you have found the 4 coloring of the other graph because you just remove edges. Yeah. If you remove edges, the 4 coloring stays 4 coloring. Because the coloring is defined by the adjacency property of vertices, but if you remove edges, a legal coloring will stay a legal coloring. And I will use that throughout. So I will kind of just zoom in immediately to triangulated graphs, which makes my life a little bit easier. And every graph can be triangulated anyway. So Tate's reduction is, first of all, look at triangulated graph. Tate's second reduction is actually kind of more fun. And Tate's third reduction is then the real key. The real key going from 4 colors to 3 colors. So Tate's second reduction is, okay, instead of looking at a problem, you can just look at the dual problem, where you just go back and put a vertex in each face and just an edge across each edge, and you get the dual graph. But if you think of having a triangulated graph, so whenever you have a triangulated graph and you put a vertex in each face and an edge crossing each other edge, what you will get as a dual, the blue one in blue here, is a trivalent one. Trivalent, every vertex has degree 3. Trivalent, okay? So every vertex has degree 3. So the 4-color theorem, the original one, is equivalent to a trivalent 4-color theorem. So planar trivalent graphs. So you restrict to planar trivalent graphs. And I give you an example of what these graphs are, for example. Here are planar trivalent graphs, right? Every vertex that you see here is of degree 3. And because they look like a spider web, I guess, I will call them webs. Okay? A web is a trivalent planar graph. I hope these examples are convincing enough. And a coloring problem for trivalent planar graphs is equivalent to a coloring to the original 4-color theorem. So we can just restrict to these class of graphs. I hope everyone is happy with this restriction. So we are now just looking at webs. Okay? Web, again, spider web. Keep a spider web in. Okay, so here's locally a web. And we're doing now a trick. This is kind of the real reduction of Tate. So Tate, what we just learned is the 4 coloring of the faces. So here are the faces, here are the faces. This is not really a 4 coloring, so let's make it into a 4 coloring. Let me make this blue and whatever is a good another color, green maybe, whatever. The 4 coloring of the faces is equivalent to the 4-color theorem. But there's also the 3-color theorem, and this is now an edge coloring. An edge coloring is as soon as you have edges and they're adjacent around the vertex, like in my little picture here. So here's my little vertex, and we have 3 edges adjacent around, as you can see. And if you have those 3 edges should get different colors. Okay, 3 colors. You have a 3 coloring, and every edge that kind of touches another edge along a vertex gets a different color. All of these are examples, right? So here around this vertex, you should see 3 different colors. Around every vertex, you should see 3 different colors. That's called a 3-color. Hope that's clear. And around every vertex, you should need to see 3 different colors. That's 3 colors. And Tate's real main result here is that the 4 coloring of the vertices is equivalent to the 3 coloring of the edges. So instead of looking at a 4 coloring of the map, you can just write down those webs and look for a 3 coloring of the edges. Hope that makes sense. 4 coloring of faces or vertices of the original problem is equivalent to a 3 coloring problem for the edges of a web. And that's Tate's main result. And I'm going to show you the proof, because the proof actually tells you, it's actually beautiful, pretty smart, actually beautiful, and it will tell you where the first color is gone, right? So there are only 3 colors left. So where's color number 4? It's kind of mysteriously vanished. And yeah, we'll see in a second in the proof. But let me make sure that this is my 3-color suffice, right? So the 3-color suffice is a proof of the 3-color theorem, which is equivalent to the 4-color theorem. Hope it makes some sense. Okay, here's several examples more. Here again, around every vertex, you see 3 colors. And there's this little condition that I kind of glossed over a little bit. We have those webs, trivalent planar, but there's also this kind of bridgeless condition. We'll come back to that in a second. A bridge is an edge in a graph that if you remove it, you have 2 disjoint components. Keep that condition in mind. It's not super important, but we'll see it later, kind of a nicer formulation. So the 3-color theorem is exactly what is written here. Oh, my friend kind of came again. It's exactly what is written here. So that not every trivalent, not every web, but every bridgeless web admits a 3-color. Okay, I hope that's reasonably clear. Excellent. So let's have a look at the proof, and we'll see where the 4th color vanishes. So first, I want to go from the 4-color, so the face coloring, to the 3-color theorem. And what you do is you identify the colors. You have 4 colors. You identify them with elements of the Klein 4 group. Here's my little Klein 4 group. Z mod 2 cross Z mod 2. Here's the multiplication table. So instead of calling them red, green, whatever, I call them 0, 0, 1, 0, 0, 1, and 1, 1. And my rule is And whenever I have a color on a face and I have another color on a neighboring face, then the edge in the middle gets the sum color, right? So here, green, 1, 0, plus whatever this is, purple, 0, 1, equals blue, 1, 1. Okay? So whenever I have something here, like 0, 0, whatever, 1, 0, and 0, 1, you can just 0, 0 plus 1, 0 is 1, 0, for example, you get the edge to the corresponding color, and so on. And yeah, so that's, you can easily check that this gets you from a legal 4 coloring to a legal 3 color. And what happens here is that in our client 4 group, the 0, 0 color only appears along the diagonal. Yeah, so the 0, 0 color, which in my notation here is this whitish color, the 0, 0 color only appears on the diagonal. So it will never appear when summing two neighboring colors, because neighboring colors are different. And that's where the forced color vanishes. It's on the diagonal of the client 4 group, but you never hit that diagonal in using this additional rule. Okay, so additional rule, just take the two colors, add them together, that's the middle color. And essentially the way back is essentially the same. The only thing you need to make sure is you need to kind of choose a nice way to split the middle color into the sum. That's essentially what you need to do. Yeah, and what you do is you just color in your graph. You have legal 3 coloring, and you just remove one color and you remove another color. So here, green, red coloring, and here red, blue coloring. You fill in the middle, right? So I fill in the middle here with the other color, with the remaining color, and then just put them all on top of one another again and use the client 4 group. So here, the top face here is filled blue, blue, that's a very nice blue, red, green, so red, let's say is 1, 0, green is 0, 1, then the sum should be 1, 1, and let's say that's yellow. What? Do with yellow. And white here is 0, 0, so whenever you have something like here, like red, and white will be red. So you're using exactly the same rule again, and you just get to kind of the backwards. It's really just reading it backwards with making a choice how to split your colors. So where's the fourth color? Where's the fourth color missing? Well, it's on the diagonal of the client 4 group, so it doesn't appear because you add 2 different elements. That's what it is, and you get a 3 coloring. I really love this proof. I hope it's not too difficult. I hope you like it as well. It's kind of really beautiful. Essentially, the edge coloring is the sum of the face colors using the rules of the client 4 group. It's kind of really cute. Right? Okay. That was Tate. So Tate did that in the 1880s. So a long time ago. I'm old and I can still say it's a long time ago. So it's really a long time ago. Anyway, and then there was not much progress. It kind of leads into a dead end, or it's an equivalent to the 4-color theorem. 4-color theorem is difficult, so there was not much progress until the 1970s, where, well, we had Tate webs before, where Temperley and Lee, in a famous paper, gave a reinterpretation of the result of Tate. At least if you read the paper carefully, having in mind what I'm going to tell you, you will find this. Temperley and Lee were 2 physicists, and it's sometimes a little bit difficult for me to read a physics paper, but essentially what I'm going to say is in that paper. You just need to read it carefully. Anyway, so we do the following. I'm defining for you a category, and that's just whatever it is. A category just here means it's just a black box. It's just some notion that I'm going to use. And I call it web. Web, hopefully is clear. Web stands for webs. And we'll see later what SO3 is. And it has just one generator, namely a trivalent vertex. There you go. So you can stack everything together. As it's a monoidal category, so you can stack everything together from that vertex in this fashion. So every little diagram, so you should think of it like a Lego box. So you know that this is a diagram, then you know that this is a diagram because you can stack them together and you can stack another one on top. And eventually you can build all graphs. So essentially every trivalent graph you can build, just formulate it as a monoidal category with 2 operations, as in my picture here, just stacking vertically and stacking horizontally. So here's the vertical stacking, here's the horizontal stacking, up to some relations. And the interesting relations are those 3. So Temperley and Lee tell you that there are 3 interesting relations. A circle equals 3. So now my category is linear. So I can talk about linear combination of diagrams. Okay. So the diagrams form a basis. And you should think of it as like adding basis vectors. And I could talk about linear combinations. So I can say that the circle, yeah, I like this arrow, is 3 times the empty web. And this is my relation here, which really just says whenever you see a circle in the diagram with whatever, you have some crazy diagram with a circle, and this is the same crazy diagram 3 times because you have removed the circle. Similarly, whenever you see a lollipop or one gun, then it's 0, and you have this funny relation, which people call H equals I. So this is the symbol H. This is the symbol I. And essentially what it says is that I is equal to H up to some error terms. So the last relation is called H equals I. Hope that's clear. So only 3 relations. It's very simple. Circle is 3, a lollipop is dead, and this is kind of a little bit like a strange H equals I relation. And we put them together in something we call web SO3. All right, I hope that makes some sense. And what you do then, okay, why would you do that? This is a good question. And that's kind of the magic of Tubbenhauer leap. You do that because having those 3 relations, you can find relations to kind of simplify every face of a given trivalent graph. So whenever you see a 2-gun here, a 2-gun is nothing else than this picture, right? So here, remember that at those points, there's always a vertex. I'm not really drawing them anymore. So this is a 2-gun. It has 1, 2 edges. It's a 2-gun in the graph, and you can simplify it in a certain way. If you have a triangle, the next difficult one, you could simplify it. If you have a square, you could simplify it. If you have a pentagon, you could simplify it. And note this funny sign here for the pentagon. Anyway, everything else is kind of a positive number, but for the pentagon, you get a funny sign. Okay, fine. But you can simplify faces. Whenever you see a face in a web, you can simplify it in this category as a linear combination of other webs. And this gives you a way to kind of simplify every web. For example, if I have this web here, it's called a theta, because if I would draw it nicely, let me draw it like this, it looks like a theta. So it's trivalent, as you can see. So it's really just a web. And I can simplify it now until I hit the trivial web, the empty web, because what I see here in my little box, if you just turn your head, this is actually this one here, right? It's a diagonal. So I can simplify it. So this is 2 times, and then the diagonal goes away, and what remains is a circle. And this is then 6 times, so 2 times 3 times the empty web, right? So you can evaluate all webs to a number, having those rules. That's called a web evaluation. And that's essentially done by Tubbenhauer leap. And they say, okay, web evaluation counts the number of 3 columns. Okay, so you take a web, apply those rules, every step simplifies the diagram, so eventually you will hit the trivial diagram, and then you're done. You get a number, whatever it is, 12. And the number you get is the number of 3 columns. So this actually not just kind of shows that there are 3 columns, but also counts the number of 3 columns. I will just show you another example in a second. But you might wonder why actually are, well, there's a 1-gun relation. Remember, we had a 1-gun, we had a 0-gun, we have a 1-gun, right? We have a 2-gun, we have a 3-gun, a 4-gun, and a 5-gun. But I never told you a 6-gun relation, I never told you a 7-gun relation. Why on earth is that enough? Because there's an Euler characteristic argument, it's a beautiful soccer ball argument, that every closed web, so it's really just a closed picture, whatever, something like this. Here's a web. Every closed web will contain smaller or equal than 5-gun, and it's essentially the same proof as that you can't build a soccer ball out of hexagons. There will always be a 5-gun on soccer ball, and note that the soccer ball really is a web because at around every vertex you have 3 adjacent edges. Yeah. Anyway, so everything contains at least a 5-gun, and we have relations to simplify 5-guns and lower, so we inductively can just burst all webs to numbers. And the number you get, that's what Tubbenhauer leap say, is the number of 3 colorings of the web, which is kind of a really cool result, right? So this gives you a way to count the number of 3 colorings of a web by just inductively bursting the faces. And the proof is pretty simple. I just sketch it here. The only thing you need to check is that the relations preserve the number of colorings. And what you need to do is you need to fix a boundary coloring, for example, purple, blue, purple, and check that on both sides of the H equals I relation, for example, and you get the same result. So this has no coloring. If this is purple, blue, there's no coloring. Similarly, this has no coloring, but these 2 have 1 coloring because you can fill in the remaining color in the middle, and you get the equation 1 equals 1, which holds true, and you just check the same running over all different colorings. I've done another example. So in this case, you get 0 equals 0, and you just check that the number of colorings is preserved under the relations, and that proves the result inductively, because our defining relation here, the circle, really just says there are 3 colors for the circle, right? There's 3 colorings of the circle, whatever. Blue, what is it? Red, green, and purple, or whatever my colors are, right? So that's why it's 3. And then inductively, the same holds for all type of faces, and that proves the statement. Again, really brilliant idea, actually, a brilliant idea, and a really simple proof. I've just checked that the number of colorings is preserved. And here I give you an example. So for example, here, if you have this web here, in the middle you see a square, you use the square relation. So where is it? So here we go. The square, where's my square? Here's my square. The square says square is equal to horizontal and vertical removal, and the sum over both of them. So here I replace the square by the horizontal, I replace the square by the vertical, and I get 1 circle plus 2 circles, which is 3 plus 3 squared, which is 12. And indeed, there are 12 colorings of that object. And you can apply that to every web. And in fact, there's an easy algorithm that you can put in a computer to apply, just count the number of 3 columns. It's kind of really beautiful. I hope this is clear. So, and then essentially what follows from Temperley-Lieb's idea is another equivalent formulation of the 4-color theorem. Every web evaluates to a non-zero scalar, because that scalar is the number of 3 colorings. And I should write here something like every bridgeless web. Bridgeless, right? So whatever. And bridgeless is exactly the condition that is captured by this identity. Because if you think about it, okay, here and here, and this is the bridge. So right, if I remove that edge in the middle, I get an unconnected graph, but I can't color the lollipop, because if I make this edge, let's say, what is it, red, and I want to make this edge blue, then I need to make this edge green, and I kind of get a contradiction. And if you now think about the face removal rules, you have some complicated web and some bridge in the middle and some complicated web, whatever, and you can apply the face removal relations, for example, on this part until you hit a lollipop. So the lollipop is exactly, the lollipop kills the number of colorings, and the lollipop is exactly kind of this bridgeless condition on the web. Okay. So then Temperley-Lieb essentially showed that every bridgeless web evaluates to a non-zero scalar is equivalent to the 4-color theorem. In particular, the 4-color theorem is immediately true. Well, maybe not quite. It's immediately true up to this funny sign here, because this funny sign ruins your positivity. If there would be no sign, there would be no constellations, and everything would just be positive. And don't worry about the 0 from the lollipop. That's kind of easy to see. So if there wouldn't be a sign, everything would be positive, and you clearly get a positive answer. And that's what you want. It's a number of colorings, and you would be done. But there is a sign, so there might be constellations, and no matter how you write the final relation, the pentagon is particle, there will be a sign. I hope it makes some sense. This is an almost proof, another almost proof of the 4-color theorem. The only bothering guy here is the sign in the pentagon relation. And to kind of keep track of that sign is the whole task you need to do to prove the 4-color theorem from this approach. But you can. So kind of you need to keep track of the sign, and you need to make sure that there's always something bigger so that the sign never gets you into some negative area. Okay, two questions remains. Can we beef this up? There's this little sign that is annoying. Can we beef that up into a proof of the 4-color theorem? The answer is yes, we can, but it's still a good bit of proof. And question 2 may be more tempting. Why on earth did Temperley-Lieb do that? Where does the relation come from? Okay, it works. It counts the number of colorings. But why on earth would anyone ever write down an H equals I relation? Why on earth? Where does it come from, right? I'm going to answer both, but I will be very, very, very sketchy for the first one, just to make sure. Okay, and the point is we take rotations SO3, right? Special orthogonal matrices, 3x3 matrices with complex entries. SO3, and you can think of this as rotations of, well, these are rotations of 3 space. I just need to take complex numbers to have an algebraically closed field. But if you want, you can think of the real SO3, which is the antipodal S2 mod the antipodal map, topologically the real version is really just this. And this is kind of my favorite picture of the antipodal map, because Australia under the antipodal map gets very wet because it fits very nicely into the Atlantic Ocean. Anyway, so this is kind of a really different thing, if you want, because there are now 3x3 matrices, and 3x3 matrices clearly act on a three-dimensional space, just taking the vector and do matrix multiplication on the vector. So I take this X and I act on it. So I have this action SO3 on a three-dimensional space. Looks completely unrelated, but I guess I wouldn't call this Yamada into live webs if it wouldn't be some relation to the original web cartoons. And it turns out there's an equivalence of categories. Yeah, they encode the same information between our little web friend, where we have the four-color theorem, and representations of SO3. So representations of our matrix group. And the equivalence goes as follows. You send a boundary to the representation X, and you send, for example, this guy to the inclusion. So here's X, and every strand you should see an X now, the inclusion of X into X tensor X. And here, for example, the inclusion of the trivial representation into X tensor X. Right? And all of these guys have a meaning in terms of SO3 representations. And it turns out that this is an equivalence of categories. In other words, our four-color theorem is equivalent to a representation theoretical fact in representations of SO3. And yeah, thank you so much, little error. Yeah, so I think this is really good. So the four-color theorem, which other area has nothing to do with representation theory at all, is actually equivalent to a representation theoretical statement. Yeah, and those relations are really just relations among SO3 matrices and SO3 equivariant matrices. That's it. So that funny H equals I relation is an honest relation in matrices. It's not just some crap people came up with, but it's an honest matrix relation. So matrix A plus matrix B equals matrix C plus matrix B. And in this case, these are 9x9 matrices because at each vertex you see a three-dimensional vector space, our defining representations of SO3. So these are just relations in matrices. And they don't come out of nowhere. They're relations in matrices. So the whole four-color theorem is equivalent to a matrix question on SO3 equivariant matrices, which I personally find is a cool way to state the four-color theorem, because it's very surprising. So where does it come from? But hopefully I explained the whole story, and kind of all the relations, like the pentagon relation, is now a relation among matrices. Okay, let's address the final question. How do you want to show positivity? And positivity can be shown as follows. If you close the relation in any possible way, and you can close it minimally, so not creating any new faces in the red part. So if you close it in any minimal way and you use the VAP evaluation, you will always get a positive number regardless of the sign. And this is an observation which will lead us to a proof of the four-color theorem. So the relation itself has a sign, but closing it, you will always see that there's something bigger than the sign, and there are constellations, but they never get down to zero. Okay? Hope that makes some sense. Closing it in any way. So put anything you want red on the boundary in the same way as I did it here. You can't do it without creating new faces. You can do it without creating new faces because you can otherwise get rid of the faces. Okay. And then we can just copy the Appel-Haken approach, and you can write down a certain number of unavoidable configurations. Here's one, it's pentagons, which is some open configuration of this form, right? It's some local configuration that sits somewhere in the disk. And yeah, so if you can check positivity for those local configurations, then the four-color theorem is true, or the three-color theorem is true, and it's equivalent then to the four-color theorem. And yeah, the Appel-Haken argument, you just copy it. It's not very difficult. It's an Euler characteristic argument again that kind of ensures that in every one of those unavoidable configurations, there is at most, I think, an 11 gun. So there's at most an 11 gun, some gun that is maximal, and there's also a bound on the number of faces you see. So if you have a bound on the number of polygons you see and the bound on the number of faces you see in total, you get only a finite list, and you would only need to run through that finite list. Every finite list has a finite number of closures. You just evaluate a finite number of things, and you just need to check whatever you get is a number bigger than zero, and that's equivalent to the four-color theorem. It's not very exciting again, because as I said, well, there's still a computer proof involved. There are plenty of cases to check. There are plenty of closures to check, but it's pretty straightforward. You just evaluate it and you get the number, and you need to check that the number is bigger than 0. Right? It's still essentially the proof of Appel and Hacken, but now formulated in terms of Webb's or representation theory, which gives it a different flavor, which I think is already worthwhile to do. And yeah, so that's where it goes. The A holds if and only if finally many things evaluate to positive numbers, and just check B via computer, and hooray, hooray, 3 colors suffice. So you can really do that with a computer. You just have plenty of cases to check. It's a little bit too much to do by hand, but in principle, pretty straightforward. It's just you end up with too many cases that you can't check by hand. I hope this is a convincing argument and will eventually give you a proof of the 4-color theorem. Note again that we would be immediately good if there wouldn't be a negative sign in the pentagon. But there is a negative sign in the pentagon. Life is just bad. Life is just a piece of shit. So you need to check whatever how many cases. And yeah, well, I can't do that by hand, so I could use a computer. Turns out that there's a even more representation theoretical statement which is equivalent, which I'm going to tell you very briefly, and then I stop. What you also can do is you can just realize that our X is a 3-dimensional space, so you can give it a basis that you could call purple, blue, and green, for example. You give it the 3 colors, and then a coloring is essentially the same as a certain coefficient in this matrix is non-zero, and then you can check A is equivalent to C, finally many inequalities on matrix entries. And it's like quite easy to check. You just have plenty of cases you need to check, and quite large matrices you need to check. But essentially, it's just you have matrix A, you have matrix B, you need to compare them, and you need to say that entry is in matrix A is smaller than entry in matrix B. And then you're already good. And you can also just check that. And this is also really nice explanation where the colors come from. They're just the basis vectors. The 3 colors are just the basis vectors for defining representation C cubed. Anyway, I hope you enjoyed this story today, and I will hope to see you next time.